This is 3, 3. Dividing polynomials. Now, way back in the beginning of the book, a chapter that we never even touched, I think it's in P4, you deal with adding polynomials, subtracting polynomials, and multiplying polynomials. And you get put off on division until here, chapter 3. Most people do okay with this. How do you divide 23 into 731 without a calculator? So how many times does 23 go into 73?
3 times.
3 times. So you go 3 times 23 is 69, right? So that's a remainder of 4, right? Yeah. And then bring down the 1. And then how many times does 23 go into 41?
Once.
Once. So you put a 1 up there, you put 23 down here, and you subtract it, and you get? Oh, 18? 18? 18. All right, so questions. Ready? Ready. 4th grade terminology. What's the 23 called? Close, no cigar. Divisor. What's the 31 called? Quotient. Quotient. What's the 18 called? Everybody knows this one. Remainder. Woo! 1 out of 4. What's the 731 called? Someone said it earlier. Dividend. It's called the dividend. So basically what this turns out to be, if you want to write it as a multiplication problem, is if you take 23, you multiply it by 31, and you add 18 to it, this becomes 731. As a multiplication type problem. This is actually called the Euclidean, not Euclidean, what is it called? No, Euclidean. Oh, I can't remember the name of it. Dang it. It's a number theory thing. And
It's okay. You get
that's really sad that I can't remember the name of it. I used to teach it all the time. Oh well. Also, we can look at this as a whole number plus a fraction. What's the fraction? Close, no cigar. Let's flip it around. 18 out of 23. So the remainder becomes part of the answer. When they taught you to put R18, that's probably the worst thing in the world to teach a student, because what does it mean? It means absolutely nothing as an answer. But 18/23 actually means, 18 out of 23. So the proper answer is really 31 and 18/23. All right, so that's long division with just plain old numbers. But you have to remember, when we're dealing with algebra, anytime we put an x in there, x also represents a number. So we should be able to take a polynomial and divide it into a polynomial. Why the heck would I want to do this?
something like.
How horrible of me. Okay, so how do I do it? Well, I pretty much do it the same way. I put something on the top that when I multiply it down, makes the number smaller than what I'm dividing by. The hard part here is we don't really know what the number is because we don't know what x is. And the second thing we have to remember is anytime I do this product, I have to take it away in those positions. So I'll multiply it down, take it away from what's above it. Okay. So here's the trick. You only concentrate on the first terms. You don't look at any of the other terms. You concentrate on the lead coefficients and lead terms of these polynomials. And you pretty much say 2x on the outside goes into 2x cubed, or what times 2x is going to give you 2x cubed? Your answer is? X squared, right? So you put x squared up here, and you have to remember that you're multiplying all of 2x minus 3, so it's going to hit the 2x, but it's also going to hit the 3. You can't just do one and not the other. So it distributes. So x squared times 2x is 2x cubed. X squared times negative 3 is negative 3x squared. And it's really important to line up your powers. If you're missing a power, you have to actually move it over or put a 0 in there. All right. Now this green part that I just wrote down, what's the next thing I need to do to it? Subtract it. And I have to subtract the whole thing. Can't leave any piece off of it. Now the easiest way to subtract a polynomial is just go through and change its signs. So change the outside one to plus, make the 2 a minus, make the 3 a plus. Distribute the negative and change the signs. And then just add. The cool part is, what happens to the 2x cubes? They become 0, and you know you're on the right track if that becomes 0. The next one is negative 13x squared plus 3x squared. Negative 10x squared. All right, then what? Yeah, kind of like how we brought down the 1 over there, we're going to bring down 23x. Don't leave off the x. We need that. And you start all over again. What times 2x is going to give me negative 10x squared? Negative 5x goes up here. And you distribute it over the 2x minus 3. So negative 5x times 2x is negative 10x squared. Negative 5x times negative 3.
Negative 15.
Positive 15, right? Negative times a negative. So positive 15x. But I'm going to have to take this and technically change all the signs. I'm going to subtract it. So change all your signs. Put minus this whole thing, but then go through and change all the signs. And then add them together. What happens to the 10s? 0. 23 minus 15.
8.
This becomes 8x. And drop down the next number, which is negative 8. Okay. What times 2x is going to give me 8x? A positive 4. Make sure you say positive or negative because that actually gives you your operation. If you just put 4 up there, it makes no sense. So either positive 4 or negative 4. So positive 4 times 2x is 8x. That's expected because I want those two to cancel. Positive 4 times negative 3 is negative 12. But then I want to take the whole thing and subtract it. Which means go through and change all the signs. So this becomes positive, this becomes negative, this becomes positive. And then add it together. 8's go away. Negative 8 plus 12, 4. Change markers here. This is 4. So when I write my answer, there's two ways of writing it. I can write it as a product plus the remainder is equal to the dividend. So that way would be 2x minus 3 times x squared minus 5x plus 4 plus that 4. And this would equal the original polynomial. 2x cubed minus 13x squared plus 23x minus 8. So that's one possible way of writing the answer. There's a reason to write it this way, and we'll come back to that a little bit later. Okay. The other way of writing it is as a fraction. The whole part of your answer is the x squared minus 5x plus 4 plus the remainder. Well, what's the remainder? Just 4? 4 over the divisor. So 4 over 2x minus 3. And that's the other possible answer. This is the one most textbooks want. But it's the top one that's more important, which is interesting that textbooks don't teach it that way. If you just write this as the answer, it kind of makes sense of where you want to go with it. But this one is very clear when you do it this way, write your answers this way. What happens if the remainder is equal to 0? See here, you don't really see what's going on if the remainder is equal to 0. You see the polynomial then would just be the first 3 terms. But here, if the remainder is equal to 0, that 4 is gone. And what have you done to this polynomial if you can write it in 2 polynomial terms? What's this called when you take a polynomial and write it like this? It started looking ugly, really expanded form. This would be called factored form. So if we can get the remainder equal to 0, we can start factoring things that have higher degrees than 2. We could do 3, 4, 5, as high as we want to go, which is kind of cool if you think about it. So that's our goal. We want to be able to factor these ugly polynomials into separate little linear terms. That's as far as I'm. But if you see one, you see them all. All right, so we did the long division. So let's do this one. 3x cubed plus x squared minus 38x plus 24 all divided by x plus 4. Now if I want to divide polynomial by polynomial, this is 3, 3 continued. I have to switch it into long division. Let's go through the names again. What's the bottom called in long division? What was that? Divisor. It's the divisor. The top is dividend. When you get an answer on the top of the long division, it's called quotient, and the bottom number is remainder. So divisor into dividend is going to create a quotient and a remainder. Do you remember what the first step was? You were all sleeping at that time in class. That's fine, that's fine. What times x is going to give you 3x cubed? 3x squared. So you put that on the top line. 3x squared. And just remember that you have to distribute whatever you put on the top line into the divisor. So 3x squared times x, of course, is 3x cubed. 3x squared times 4 is 12x squared. What do you do with that? Why is people whispering again? Say it louder. Subtract. Wow. I whisper class. Not one of you is confident in your answers. I shouldn't scare
That's what I was
you.
just thinking. You're scary to me.
Oh, I'm sorry. Nice.
Big and shiny.
So,
Red.
change all your signs. This becomes positive, this becomes negative, this becomes negative. The 3x cubes are going to cancel. They should. If they don't, you did something wrong. X squared minus 12x squared. Negative 11x squared. Then what? Bring down that negative 38x. And you start all over again. What times x is going to give you a negative 11x squared? Negative 11x. Put it up top. Distribute it through the x plus 4. So you're going to get a negative 11x squared. I expect that. And then you're going to get a negative 11x times 4, which is a negative 44x. Take that and subtract it away. So it's just very repetitive. Every step of the way is just doing the same thing as before. Go through, change all your signs. The negative becomes positive, negative becomes positive, the negative becomes positive. The 11x squares are going to cancel. They should. Negative 38x plus 44x. 6x. And then bring down 24. Just start all over again. What times the x is going to give you 6x? A positive 6, so put a positive 6 here. 6 times x is 6x, 6 times 4 is 24, and I'm going to subtract it away, and I'm left with nada, 0. Now if you remember anything about remainders of 0, say 5 goes into 250, how many times? 50. If you put 50 up here and go 50 times 5, that's 250 and it has a remainder of 0. The language behind that is it goes in evenly. What does it really mean though? this is important. When it goes in evenly, that means the two numbers that are chosen multiply together to give you, well, 250. So this means that I've taken 250, and now I can write it as 5 times 50. What are these called of 250? If I take 6 and I write it as 2 times 3, what are 2 and 3 called? Say it louder.
Factors.
Wow, that's exciting.
That's scary.
They're called factors. So when you do this long division and you end up with a remainder of 0, this is the important thing of this whole chapter. If you get a remainder of 0, you have actually factored the number. So because we got a remainder of 0, we can say that 3x cubed plus x squared minus 38x plus 24 is indeed equal to our divisor, x plus 4, times our quotient, that mess up there. So I've just taken a cubic polynomial and broken it down into a linear factor and a quadratic factor. And if I set this equal to 0, I can find the solutions of all x's, because it is quadratic. That makes the entire polynomial, the original one, equal to 0. We can go back to those zeros of a polynomial. It's even quite possible that the second one factors, but I don't think so. Factors of 18 that add up to 11. Oh. No, I was thinking 3 and 9. It's 2 and 9. It does factor. I don't want to factor it though, but it does factor. Okay, the other thing that is, well, troublesome in this whole problem, way too much writing. Remember what I said earlier? Mathematicians are very lazy. So there's a lot of overlap. Writing these down is actually quite pointless because each and every one of them is 0. They just disappear. Writing down x cubed, x squared, and x for this whole problem is pointless because they just line up and combine anyways, and your last number is not going to even have an x in it. It's just going to be 0, 1, 5, whatever the remainder is. And another thing that's kind of interesting if you think about it. What is that number? Oh my lord.
3715.
Oh, is that how you read it, really?
3,007.
3,715. How do I know that 3 represents thousands? It's in the thousands place, that place value system. So we can write this as this. And this would be its true value, without knowing what the place value system is, that would be its true value. Another way of writing 100 is what, though? Just trying to make you see something different. What's another way of writing 100? What times what equals 100? 10 times 10, and 10 times 10 is better known as? Well, I know 100, but put an exponent on it. 10 squared. What about 1,000? 10 cubed. So this would be 3 times 10 cubed, plus 7 times 10 squared, plus 1 times 10 to the first power, I'll write it in there, plus 5. So here's what I want you to think. Look at this. 3 times something squared plus 7 times something squared plus 1 times something plus 5 is kind of similar to this polynomial over here, where x would be equal to 10. This would be 3 times 10 cubed plus 10 squared minus 38 times 10 plus 24. Polynomials are a perfect replacement of the place value system in a weird way. So they should somewhat behave similarly. For instance, we don't write this for 3,715. We write 3715. I want to do the same thing to polynomials. So I want to write this polynomial as 3, 1, negative 38, positive 24. And just understand that as the place values move from right to left, the power on the x is increasing by 1 every time I move it. Alright, so let me write that down.
I like it all the way. It's not-
Oh, no, trust me, this is much nicer. 3, 1, negative 38, 24. This will allow you not to do all this work over here.
Well, I'll do that one.
Oh, no, you don't want to, because you're going to have to do about 30 of
It's just like
these.
simple, I
No, you're going to have to do about 30 of these for one problem.
Oh, okay.
You'll want that better. Okay, trust me for a second. All right, so that would represent the dividend. The divisor, we can ignore the x because the x really had no problems other than canceling out all these things going all the way down, the 3x cubes, the 11x squares, and the 6x's. So the x is really quite irrelevant. It was the second number that gave us most of our answers, the positive 12, the negative 44, and the positive 24 here. So what I want to do is I just want to use the 4. Also, these minuses all the time, that's kind of redundant. Just, change all the signs, change all the signs. So instead of putting plus 4, I'm going to use minus 4. Change all the signs right away. So I'm going to put a box here. That becomes minus 4. Draw a line. It kind of flips the division upside down, but it makes life a little bit easier. All right, the first part of this answer was 3x squared. But we're really only interested in the 3. Whatever goes here, I mean, if this was 5x to the 5th, you would put 5x to the 4th up here, and the lead coefficient would be 5, because times x is not going to change the coefficient. So the first part of our answer is drop the 3. The 3 just falls down, becomes part of your quotient. All right. What do you think I'm going to do with the negative 4 and this 3 at the bottom? Multiply it. Because the next number up was 12. So negative 4 times 3 is negative 12. Add these two together, what do you get? Negative 11. And if you go back to the original problem, here's negative 11. Right there. All right, do the same thing. Negative 4 times negative 11. 44. What's negative 38 plus 44? 6, which is right here. So we're getting the same numbers that we were getting with this long division in this just number evaluation. It's called synthetic division, by the way. All right, next one up. Negative 4 times 6. It's negative 24. And if you add these two together, you just get a remainder of 0. And then you just have to go back to, how do I get the answer out of this? Well, the answer is place value system. The 0 is your remainder, so you can ignore him. The 6 is your constant. The 11 would be power of 1, so this is x to the first power. And then you come to the 3, and that's x to the second power. So this pops out as 3x squared minus 11x plus 6 is our quotient. Isn't that neat? Takes up a lot less space, a lot less writing, a lot less calculations and changing signs and all that mess. So synthetic division is the way we're going to go with this. All right, get rid of all this. So let's make up something. I don't know how well this is going to work, so you might have to be slightly patient. 5x cubed minus 3x squared plus 2x minus 4, all divided by x plus 2. And I don't want to do this with long division. I want to do it with synthetic division. So what do I do with my dividend? Well, I write it down as a place value polynomial. The first number is 5, x cubed, right? But I'm just going to write the 5. Minus 3. Don't get them too close together, because if you see 5 minus 3, you might replace it with 2. Don't do that. This is not calculation. This is just a place value system. Next number up is 2. Next one? Negative 4. And I want to synthetically divide by what? 2 or negative 2? Negative 2. You want to change the sign to take care of all those subtractions. Draw a line. Drop the first number. He's guaranteed to be part of your first answer, as long as this number right here is 1. This does not work on divided by 3x plus 2. Then you'd have to do something a little fancier. But we're not going to get into that. All right, and then just start your problem. Negative 2 times 5. So you multiply this way and add the other way. Negative 10. Negative 3 plus negative 10. negative 13. Negative 2 times negative 13.
26.
Positive 26. Plus 2.
28.
28. Negative 2 times 28. Negative 56. Plus a negative 4. Negative 60. Alright. And then you just write your answer down. There's 3 numbers here. 3 numbers means quadratic. 4 numbers mean cubic. 5 numbers would mean power of 4. It's always going to be one less than how many numbers you're dealing with, the degree of the polynomial. So if you have 3 numbers left in your quotient, it's definitely going to be a quadratic. And then you have to just write it as what the remainder part. So how do I deal with the negative 60? It's negative. It's minus 60
Over x plus 2.
over x plus 2, what you divided by. So this would be the quotient and the remainder after that long division. So it makes it rather quick, easy. Most people like synthetic division. Where do they screw up? Signs. Pluses and minuses kill people. I have seen people go negative 3 minus 10 is negative 7. Even though they're both negative and you're supposed to add it. So be really, really careful with your integer work. And take your time if you're bad with it, or use your calculator to get through it.
I think you said not to write like that. I wish you had changed that.
What's wrong with it?
I don't know, I wish you had
Oh,
changed
the
that.
answer?
Yeah.
I'm using synthetic division to come back with my polynomial answer. But I don't work with my x's in the synthetic division. I just bring them back at the end. Does that make sense? Okay. We'll do a ton of these, don't worry. This one. X to the 4th minus 2x squared minus 5 all over x minus 1. Now before we do this, is there any difference between these 3 numbers? 109, 19, and 1009.
Yeah.
Heck yeah. Which one would you want to check paid to you in? 1009. Which one do you want to pay someone? 0. The 19 would probably be the smallest one. So if you're missing a power, it's replaced
Put
with
0.
zeros, right? Well, when you look at that polynomial on the top, the x to the 4th minus 2x squared minus 5, you have to be very careful with the synthetic division. It's a place value system. So what's missing in that top polynomial?
X cubed and x.
X cubed and x. So where x cubed is and where x is, they must be
0.
zeros, just like 1009. So when I do this synthetic division, I'm going to get a lead coefficient of 1. My x cubed is missing, so I'm going to put in 0. It's really important that you do this because if they don't line up perfectly with the powers, your answer is going to be way off. The next coefficient is negative 2. That was x squared. Now x is missing, so we're going to put in 0. And then the last one is negative 5. So if there's missing powers, even with long division, if there's missing powers, you have to put in a 0. All right, put a box here. What number goes in it?
1.
1. One of these days you're going to say the right answer.
I know.
1. Draw a line. First thing,
Put the 1.
drop that first number, 1. 1 times 1 is?
1.
1 plus 0 is?
1.
1 times 1 is? Negative 2 plus 1 is?
Negative 1.
Negative 1 times 1 is? Negative 1 plus 0?
Negative
1 times negative 1? And the remainder is? Negative 6. Okay. So, when I look at my quotient, a bunch of 1s, but it's kind of boring. What is it? What's the degree of this polynomial? There's 4 numbers, so the degree is 3. So this must be 1x
1.
cubed plus 1x squared minus 1x minus 1. Don't forget your remainder, minus 6 over. x minus 1. And that would be our solution of the top polynomial divided by the bottom polynomial is equal to this polynomial minus remainder. Not that bad, right? Like I said, most people get this as just the signs that they screw up. Or the multiplication, you do things like 2 times 3 is 5, or 2 plus 3 is 5, 6, weird things. So just be really careful. Which one? Well, let's do this one. It's actually easier. What if I said f of x is equal to x to the 4th minus 2x squared minus 5? Okay. And I want you to find f of 2. How would you do it?
I 2 in the place of x.
So you get 2 to the 4th minus 2 times 2 squared minus 5. 2 to the 4th. Oh, 16. Minus 2 times 2 squared. What? I couldn't quite hear. My recording device didn't hear that. Oh, negative 8. Minus 5. So that's what? 8 minus 5, better known as? 3?
I was used to negative 8 minus 5, so
And like I said, the biggest mistakes over here are sign. Alright, let's do it another way. Let's put 2 here. Let's put 1, 0, negative 2, 0, negative 5. We'll see what happens if I synthetically divide by 2. This is kind of neat what happens. 2 times 1. 2. 2 plus 0. 2. 2 times 2. 4 minus 2. 2 times 2. Plus 0 is 4. 2 times 4. 8 minus 5. 3. You get the same answer. F of 2 up here was equal to 3, and synthetically dividing by that x equals 2, I get an answer of 3. This has a neat little name. It's called the remainder theorem. Yes, you need to know this one. Star. You're going to have tons of theorems that you need to know. I think 5 of them. Well, intermediate value theorem from last time. Remainder theorem will be another one that we deal with, and then there's a couple others after this. So it goes like this. Given p of x is a poly, and p of x divided by x minus, how do I want to label this? A, x minus a, sure, why not? Has a remainder of r, some number r, like over here it was 60, negative 60, no big deal. Oh, then p evaluated today is also equal to r. So pretty much what it says is, you can do 2 things. Number 1, you could do synthetic division, find the remainder to evaluate the function at that point, or you can just evaluate the function at that point. So when does this come in handy? Well, it comes in handy anytime your degrees are higher than 3, I would say. You get a high degree powered polynomial, you don't want to be plugging in 2 to the 5th power minus 5 times 2 to the 4th power. It gets very cumbersome to calculate without a calculator. So this just gives you another way of calculating out a polynomial, evaluating a polynomial function at a point. It also turns into a what they call SAT question. SAT questions are really famous. It'll say something like, for example, is x minus 1 a factor of x to the 7th minus 1? This is an SAT question. And if you learn synthetic division and that's how you learn how to factor, the first thing you would set up is the synthetic division. So you'd go 1, x to the 7th, x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x to the, I lost where I was, 7th, 6, 5, 4, 3, 2, 1, and then the constant, right? Then you synthetically divide by 1. That takes up a lot of useless time. So instead of synthetically dividing, we can go the other direction and take the number and plug it into the function and see what happens. So if you take the number, what's the number that we would synthetically divide by? Well, it's 1. If I plug in 1, what's 1 to the 7th power? 1. What's 1 minus 1? Has a remainder of 0, therefore it is a factor, and you're all done. So that theorem is actually kind of powerful in both directions. It's really neat. All right, how are we going to use it? Since you're never going to take the SATs again. Oh, first off, semi-proof of that statement. Let's say I just have ax squared plus bx plus c is divided by x minus x minus, oh, I don't know, m. X minus m. All right, and I want to set up a synthetic division with it. So the coefficients would be a, b, c. And I'd be synthetically dividing by m. Put m here. Draw a line. What's the first thing that happens? Drop the a. And you go, m times a is? am. And you put it under the b. What do I do with those two?
Subtract.
Add them. So this becomes am plus b. Then what? Multiply by m. What's m times am plus b? am squared. Just plus b?
Plus MB.
mb or bm plus bm. Alright, then what do I do with the last two? Add them. So you get am squared plus bm plus c. And if you look at this, and you look at the original quadratic, it's exactly the same, except wherever there was an x, I replaced it with m. So that just becomes, you know, if this was p of x is equal to this mess, then this thing here is p of m. It's a polynomial evaluated of m. So that's kind of a semi-proof of why the remainder theorem works. All right. Should use this eraser. So why not? Let's do this one next. Factor theorem. It actually uses the Euclidean division algorithm. Euclidean division algorithm. So what I'm going to state is now if I have a p of x divided by x minus a, I'll stick with the a. This is going to equal a quotient plus a remainder. If I do this properly enough, that's what it's going to equal. Quotient plus a remainder. That's our way of doing it. It's not the Euclidean way of doing it. Ooh, I gotta be careful. Hold on. Over x minus a. That's our way of doing it. The Euclidean method multiplies both sides by that x minus a. Now when you multiply everything by x minus a, you get p of x on the left-hand side is equal to, now remember you got to multiply every single term by x minus a, so you get qx times x minus a. So I'll put the x minus a first, times q of x. When I multiply x minus a times r over x minus a, it just becomes plus r. And that's the setup of Euclidean division. It shows you the product plus the remainder equals the original dividend. Equals the original dividend. So what I'm saying is, well, what happens if r is equal to 0? Well, what did I just do to p of x? Well, then it becomes p of x is equal to, let me write here, if r equals 0. You get p of x equals x minus a times q of x. What did I just do to p of x? The remainder is equal to 0. What's it called? Factors. So this is factoring p of x. So the factor theorem pretty much states if you take a polynomial function and divide it by a linear factor, and your remainder is equal to 0, then you have just factored your original polynomial into the linear factor times the quotient. That's pretty much all it says. I'm not going to write down all the words. That's pretty much the proof of it. It's pretty simple. It comes back to the remainder theorem, and it kind of attaches one more piece to it. All right, so that's the important part. When is it equal to 0? Is this one work? I hope so. It has 2 questions, so it's not horrible.
You fail.
Yeah.
The quiz only has 2 questions.
Yeah. Oh, that's right. We're in trouble.
Let me write this problem down. I think one thing that scares people about this chapter is the length of these polynomials. You're so used to working with quadratics that I'm extending it by a few terms here. So here's a polynomial. Don't let it scare you. It's just a polynomial, and we're going to break it down into just coefficients anyways. And I'm going to tell you something about this polynomial. P of x has a factor of, what was it, x plus 3. And what I want you to do is completely factor p of x. Break it up into all its possible linear factors. All right, so I'm telling you that it has a factor already of x plus 3. So what should you do? You take the remainder theorem and the factor theorem, you put them together. If I know it's a factor, then I know it's going to go in evenly, and what will be left behind is another polynomial that is smaller in degree than the original one. So what I want to do is I want to synthetically divide p of x by x plus 3. So I can break it up into its quotient and remainder. And the remainder should be 0 because it is a factor. Okay. So what are the coefficients of the dividend? In other words, p of x. 1, 4, 2, negative 0, negative 3. And we're going to synthetically divide that by the divisor. And the divisor is x plus 3, so what do I put in the box? Negative 3. Draw a line and do your synthetic division. Drop the first one. Drop the first coefficient. Multiply. Negative 3 times 1? Negative 3. Negative 3 plus 4? 1. Negative 3 times 1? Negative 3. Negative 3 plus 2? Negative 1. I chose the right problem. We'll find out. Negative 3 times negative 1? 3. 3 minus 4? Negative 1. Negative 3 times negative 1? Positive 3, and then positive 3 minus 3, of course, is 0. It's what I expected anyways, but it's nice to know that it actually works. So this has a remainder of 0. So by the factor theorem, that says that the factors of p of x can now be written as x plus 3, the divisor, times the quotient. Well, what's the quotient? How many numbers are in the quotient? 4. So the degree is 3. So this would be 1x cubed plus 1x squared minus x minus 1. And then the remainder is 0. So I don't have that plus r over whatever. But this also says to completely factor p of x. Is that completely factored? No. So can you factor x cubed plus x squared minus x minus 1? Group them. Group the first two. What can I pull out? X squared. What's left behind? X plus 1. Never shrink the number of terms that you're pulling out from. It always is the same side, 2 terms. What's the GCF of the second two? Negative 1. What's left behind? X plus 1. What can I kick out of those two? X plus 1. So now we have x plus 3 times x plus 1 times x squared minus 1. Is it completely factored?
No.
Heck no. What can factor more?
X minus 1, x plus 1.
The back end there is x plus 1 and x minus 1. So p of x is now equal to x plus 3. If this one is x plus 1, x minus 1, and I already have an x plus 1, that becomes x plus 1 squared times x minus 1. Cool. Review time. Graph it. Well, at least a sketch of it. Good thing we know what the degree is right off the top of the bat. What's the degree of this graph? P of x. Degree?
3, 2.
You tell me. Don't be guessing. Go back to the polynomial. Here's P of x. Up here. What's the degree?
2. Oh, 4.
4. The number right there, 4. So the degree is 4. What's the end behavior of a fourth degree polynomial that has a positive coefficient? Whisper. What?
Repeat the question.
End behavior of a fourth degree polynomial.
Both sides up.
Both sides up. So it's up, up. So the end behavior on this thing is going to be up, up. And then something weird is going to happen in the middle. All right, what are the zeros?
Negative 3, negative 1, 1.
What do we call the factor of negative 1? You remember? I only wrote it down on the board once last time. Because it happens twice. Because it's x plus 1 all squared. So that negative 1 has a fancy name. It's a multiplicity of 2. Some textbooks will write this as negative 3, negative 1 times 2, 1. Kind of like that. Where it says negative 1 is the root and it happens twice. It happens twice. So that's another way of designating it. Alright, so let's graph it. XY axis. That's what happens when you come late.
How you doing?
So my x-intercepts are negative 3, someplace over here, negative 1, and positive 1. And the end behavior on this thing is up, up, right? So it's up on the left, and eventually it'll be up on the right. Alright, so as we travel down towards negative 3, how does the graph behave when it gets close to negative 3? Well, negative 3 is coming from this linear factor of x plus 3. So how does it go or behave around -3. It's like a line, it just goes through it. So we're going to come down, we're going to go through 3, -3. But we have to kind of turn around eventually and go through -1. Now remember, polynomial graphs are rolling hills, so there's no instantaneous changes in direction. So we have to smoothly come back to -1. But -1 is this guy here. How is he going to behave at -1? What's that? Parabola bounce. So as we come down, we're going to have to turn around. Oops, we're going to have to turn around. We're going to bounce off -1. It's going to look like a parabola really close to -1. All right, and then it's going to turn around again because it has to hit that +1. So as it turns around and hits +1, how is it going to behave at +1? That's coming from this guy. It's going to act like a line. So it's going to come down, rotate, and end up going exactly where I expected it to go. So that would be a somewhat decent picture of P of x. Now, how far down these two little bubbles go, no clue. I guess I could find the y-intercept. Well, the y-intercept is -3. So I know it crosses the y-axis at -3. So this one probably goes down a little further. Does that. This one does that. But that's about as best I can get. Alright, so we took a polynomial. We knew one of its factors. We used synthetic division to break it up. And the polynomial that was left over as a quotient was factorable, so we broke it down and graphed it. Should I ask that on the test? Heck yeah, why not? It makes it more fun and interesting. Alright, there's one other thing. If I have P of x is equal to x minus 1, x plus 1, x minus 2, x plus 2, x minus 3. It's just some weird, ugly polynomial. Notice first off that each one of the factors is linear. Not one of them is squared. It's nothing crazy going on. What's the degree of that polynomial? 5. So the degree is 5. How many zeros does it have? Not what are the zeros, how many does it have? No zeros at all? It has 5 of them. 1, -1, 2, -2, and +3 are zeros, and there's 5 of them. So the number of zeros is 5. Interesting. What about P of x up here? P of x is a degree 4. How many zeros does it have? 3. A little bit less. But even if I changed that -1 to something else, so I'd have 4 answers, the number of zeros in the degree would match. So there's a neat little theorem, it's called the n-zeros theorem. That will tell you somewhat how many answers you're supposed to have. How many answers you're supposed to have. Given P of x is a polynomial function with degree of n, then P of x has at most n zeros. Has at most n zeros. If you convert this language into x-intercepts, a degree 5 polynomial could have 5 zeros, 4 zeros, 3 zeros, 2 zeros, 1 zero. Why does degree of 5 have no possibility of 0 zeros? Good question. What's a degree 5 graph and behavior look like? Degree 5 polynomial, what's its end behavior look like? Both up?
Down the right.
Down and up, right?
I'm gonna say odd.
Yeah, odd behavior. So if it's down on the left and up on the right, why is it guaranteed to have a 0? Anyone? Yeah, but what theorem tells you it has to cross sometime? If I have a point that's below the x-axis and a point that's above it. What is it called? That first one I did. First theorem I did. Down on the left, up on the right, up on the right, down on the right. One's above, one's below. Begins with an I. Intermediate value theorem. So if you have a degree 5 polynomial, you are guaranteed, without a doubt, to have one solution. One x-intercept. Guaranteed. If it's even, though, you have to be careful. If you have a 4th degree polynomial, I could take this green graph. Remember adding like 7 to it? What would adding 7 do to this graph? It would move it up 7 units, and it would never even touch the x-axis. So even graphs could have, in this case, 4 zeros, 3 zeros, 2 zeros, 1 0, or absolutely none. So even graphs can go down to 0 roots whatsoever. Odd graphs have to have at least 1. So that's something to keep in the back of your mind. But N0's theorem tells you how many answers you're looking for. The maximum is, what's the degree of the polynomial? So if you have a 7th degree polynomial, how many answers are you possibly looking for? 7. It makes it kind of easy, and it also tells you when you're done.